Have you ever noticed that predicting something is actually very different from explaining why it happened?
Oh, absolutely. Yeah.
Like you see a sudden drop in website traffic or, a dark cloud rolls in and you can predict what's coming next, right?
Right. You navigate based on the pattern.
Exactly. But predicting it doesn't mean you've explained the hidden mechanics of it. You haven't found the actual cause.
Yeah. And that distinction is really the core of how we understand reality. True scientific explanation, I mean, it requires exposing those hidden gears.
Exposing the gears, yeah.
Right. It demands that we distinguish a mere symptom from a genuine physical cause.
And that pursuit is exactly what we're exploring in today's deep dive. We're looking at the revolutionary ideas of the 20th century philosopher Wesley Salmon.
A truly fascinating thinker.
He really is, and we are utilizing a highly detailed entry from the Stanford Encyclopedia of Philosophy to do this. We're going to trace Salmon's lifelong, uncompromising quest to fundamentally put the cause back into because...
I love that phrase.
Right. It's his mission. And by the end of this deep dive, the lens through which you evaluate the explanations you encounter, in science, in business, in the news, it is going to fundamentally shift.
Because Salmon's work really forces us to abandon our cognitive shortcuts. He realized that modern philosophy and, well, science too, had kind of inadvertently settled for mathematical models that described the world without actually explaining it.
They were just looking at the math.
Exactly.
Yeah.
And he wanted the mechanics. He wanted to know how information, energy physically travel through time and space to, bring about an event.
Okay, let's unpack this, because to really understand the sheer intensity of Salmon's demand for physical evidence, we have to look at the massive paradigm shift in his own life.
Yeah, his background is so crucial here.
It really is. We're moving from this big abstract premise to the story of a man whose worldview just completely inverted. So Wesley Salmon was born in Detroit in 1925, and he did not start out as this hardcore scientifically grounded philosopher.
Not at all.
No, he actually attended the University of Chicago Divinity School with the explicit intention of becoming a minister.
Right. He was deeply influenced by the charismatic minister of his family's Methodist church growing up.
Yeah.
But the Divinity School proved to be this incredible intellectual crucible for him. While he was in Chicago, he experienced a really profound, systematic dismantling of his faith.
Wow.
Yeah, he didn't just lose his belief in Christian tenets, he lost his confidence in the social value of religion entirely.
That is just a staggering psychological pivot. I mean, you don't just walk away from a calling like that without it leaving a permanent mark on how you process information.
Oh, it shaped his entire intellectual trajectory.
Yeah.
Because when you abandon a worldview based on revealed truth and, unobservable faith, you tend to swing hard toward a rigorous demand for verifiable, observable foundations.
Right. You want the hard facts.
Exactly. So he transferred his pursuit of truth away from theology and entirely into philosophy. He actually earned his master's with a thesis on Alfred North Whitehead's conception of freedom. But the real turning point was his move to UCLA to study under Hans Reichenbach.
Okay, yeah. Reichenbach is the heavy hitter here, like a total giant of logical empiricism.
Huge. And Reichenbach provided the exact analytical grounding Salmon was craving after his religious disillusionment.
Because Reichenbach was all about probabilities, right?
Right. He championed a heavily probabilistic, scientifically grounded approach to epistemology. And specifically, he instilled in Salmon this frequency interpretation of probability.
Wait, break that down for me. The frequency interpretation.
Yeah, so this is crucial. To Reichenbach and to Salmon, a probability isn't just a subjective feeling of certainty or like a lack of information.
Like me guessing if it's going to rain.
Right, no. It is a hard physical ratio of actual occurrences in the material world. You don't guess the probability of a coin toss, you observe the frequency of its outcomes over time.
So it completely grounds everything in the observable world.
Exactly.
But Salmon also realized that, philosophers just sitting around in a room debating other philosophers about observation, that wasn't enough.
No, he needed to get into the weeds.
Right. So by 1963, he's at Indiana University in their newly founded History and Philosophy of Science department, and he's actively mingling with working physicists and biologists.
He's talking to the actual scientists.
Yes. And he comes to this conclusion that philosophy looking only inward runs this great risk of becoming completely sterile. To use a mechanical analogy, it's like you can memorize the owner's manual of a car sitting in an empty room, right?
Sure.
But until you go out to the garage, pop the hood, and get your hands covered in grease, you don't actually know how the engine works.
That's a perfect way to put it. And his insistence on looking outward toward the messy, real-world practice of science is what inevitably put him on a collision course with the dominant philosophical establishment at the time.
He had to tear down the old system.
He did. He realized the prevailing framework for how scientists were supposed to explain the world was fundamentally broken.
And this brings us to Carl Hempel and the received view, because in the 1940s and 50s, Hempel built what was called the covering law model.
Right.
And the core assertion of this model is something that, on its face, sounds incredibly elegant, but it falls apart instantly in practice. It's the idea that an explanation is simply a logical argument.
Yeah, Hempel argued that to explain an event, you merely show that it was logically deduced or, at least made highly probable by a set of initial conditions combined with universal or statistical laws.
So it's just math and logic.
Exactly. You state the conditions, you apply the law, and if the event mathematically follows, boom, you have successfully explained it.
I have to completely push back against the historical acceptance of that model.
Right.
Because equating a logical deduction with a physical explanation is a massive category error.
Oh, it really is.
Like, I can give you a perfectly valid logical argument that explains absolutely nothing.
Let's hear it.
Okay, let's say I point to my friend John, who is biologically male, and I state the universal law. Anyone who regularly takes oral contraceptives will not get pregnant.
Okay, tracking.
The initial condition is that John takes his wife's birth control pills every day. The deduction, therefore, John does not get pregnant. That is a logically flawless deductive argument.
It is flawless logic, yeah.
But taking birth control is absolutely not the causal explanation for why John isn't pregnant.
Exactly, and that is the exact vulnerability Salmon attacked. He called the idea that an explanation is an argument the third dogma of empiricism.
A third dogma, wow.
Yeah, and his primary objection was devastating. He basically said irrelevancies are completely harmless to arguments, but they are fatal to explanations.
Oh, I like that.
Right. In your example, John taking the pill is totally irrelevant to his lack of pregnancy. The logic survives the irrelevancy, sure, but as a scientific explanation, it is worse than useless. It's misleading.
Which leads perfectly into Salmon's ultimate takedown of Hempel's model using the barometer.
Oh, the barometer example is classic.
It's so good. So imagine you are tracking meteorological data. You observe a sudden, sharp drop in a barometer reading in your house.
Okay.
You apply a statistical law. Severe drops and barometric readings are highly correlated with the arrival of massive storms. Therefore, you deduce a storm is coming.
And under Hempel's covering law model, you have an initial condition, you have a statistical law, and a high probability deduction.
Right.
So you haven't just predicted the storm. According to the received view of the 1950s, you have just explained the storm.
But the barometer dropping clearly doesn't cause the storm. A needle moving on a dial in my living room doesn't generate atmospheric turbulence outside.
Right. It's just a dial.
Exactly. We confuse predictive signs with root causes constantly. A stock market indicator crossing a moving average doesn't cause a market crash. A dry cough doesn't cause a respiratory virus. It's just a symptom.
Yeah, and Salmon also highlighted the failure of temporal asymmetry in Hempel's model.
Temporal asymmetry.
Yeah, so logical arguments are completely indifferent to the flow of time. You can use an argument to retrodict the past just as easily as you predict the future.
Oh, interesting.
Right, so you can say, there is a massive storm currently happening, therefore the barometer must have dropped an hour ago. The logic flows perfectly backward.
But physical explanations don't work like that.
No, they are strictly asymmetrical. They only flow from cause to effect, from past to future.
Right, so the sudden drop in atmospheric pressure explains the dropping barometer, and it explains the storm. Neither the storm nor the barometer can explain the drop in pressure.
Exactly.
So if Hempel's model is this flawed, how do we actually systematically fix it? I mean, if we want to map actual reality, how do we weed out the fake causes, the barometers, and the birth control pills from our data sets?
Where Salmon's first structural solution was the statistical-relevance, or SR, model. He shifted the focus entirely away from logical deduction and toward mathematical isolation.
Mathematical isolation.
Yet to explain an event, you must assemble all and only the factors that are statistically relevant to it. You continuously subdivide your data into what he called a homogeneous reference class.
Until what?
Until every single property left makes a mathematically verifiable difference to the outcome.
Got it. And the mathematical tool he uses to eliminate the symptoms is called screening off.
Right. Let's use your barometer example.
Okay.
Let the barometer dropping be B. Let the storm be S. And let the actual drop in atmospheric pressure be P.
Okay, B, S, and P.
Initially, B is highly correlated with S. The barometer predicts the storm. But if you factor in P, if you already know the atmospheric pressure dropped, then the barometer reading B provides 0 additional predictive power regarding the storm S.
Because you already have the root cause.
Exactly. The probability of the storm happening given the pressure drop is identical whether you look at the barometer or completely ignore it. Therefore, the actual pressure drop, P, screens off the barometer, B.
So the true cause renders the mere symptom mathematically silent. You isolate the variables until the barometer is just forced out of the equation entirely.
You got it.
You know, this screening off concept is the exact mechanism we use when our intuition detects a hidden variable in daily life.
Oh, for sure.
Let's look at the classic mumps scenario from the source material. Suppose my two kids, living in the same house, both contract the mumps on the exact same Tuesday.
Okay, poor kids.
Right, terrible Tuesday. Now, mumps has an incubation period of a couple of weeks. It is statistically absurd to suggest they caught it independently on the exact same day by pure chance.
Yeah, the odds are astronomically low.
Furthermore, because they presented symptoms simultaneously, they couldn't have transmitted it to each other that morning. So what's going on?
What's fascinating here is how this scenario perfectly triggers Reichenbach's principle of the common cause, which Salmon incorporated into his work.
The common cause.
Right, Reichenbach stated that whenever an improbable coincidence occurs, there must exist a common cause hidden upstream. And the mathematical structure defining this is the conjunctive fork.
We hunt for the hidden denominator.
Exactly. The common cause in your conjunctive fork is that, say, 2 weeks prior, both of your children attended a birthday party with a highly contagious third child.
Oh, the birthday party, always a trap.
Always. So that party is the common cause that splits off like a fork into the two simultaneous infections. And mathematically, the birthday party screens off the correlation between your two kids.
Because once you isolate the variable of the party, the fact that sibling A got sick gives you no new statistical information about whether sibling B got sick.
Precisely. The common cause absorbs all the statistical dependency.
Here's where it gets really interesting, though, because Salmon realizes that as elegant as the SR model and these conjunctive forks are, they are still just math.
Yeah, that was his realization.
Like, statistics describe reality, but they don't physically interact with it. Numbers on a page don't transmit a virus at a birthday party.
No, they don't.
To genuinely put the cause back into, because we need physical mechanisms, we have to transition from mathematical correlations to continuous physical processes in space and time.
And this represents the major evolution in his philosophy. He defined a genuine causal process as a spatiotemporal continuous entity that has the intrinsic capacity to transmit information, structure, or causal influence.
That's a mouthful.
It is, but he anchored this in Bertrand Russell's at theory of motion.
The at theory.
Yeah, which simply states that an object moving from point A to point B just consists of being at the intervening points at the intervening moments.
Oh, I see.
He wanted to eradicate any spooky, unobservable ideas about metaphysical causal powers. Just physical presence at a time and place.
But wait, if everything moving through space is just at a sequence of points, how do we distinguish a genuine causal process from a fake one? Like if a car drives down the street and its shadow moves along the pavement next to it, both the car and the shadow are moving through space and time.
Yeah, they are. And Salmon developed the Mark method to solve exactly that.
The Mark method.
Okay. He used the thought experiment of a rotating spotlight. Imagine a circular room with a spinning spotlight in the center. The light casts a beam to the wall, creating a bright spot that races along the circumference of the room.
Okay, I'm picturing it.
So you have two moving processes. You have the beam traveling from the center to the wall and the spot moving along the wall.
And to determine which is the genuine causal process, we intervene. We introduce a mark.
Exactly.
So I take a piece of red glass and place it directly in front of the spotlight at the center. The beam turns red, and consequently, the spot on the wall turns red. The beam has successfully transmitted that mark the red frequency of light from the source all the way to the destination.
Right. The beam carries the information forward. But now, try to mark the spot on the wall.
Okay.
If you slap a piece of red cellophane onto the plaster, the white spot of light will turn red for a split second as it sweeps across your cellophane.
Right.
But the moment it moves past the cellophane and hits bare plaster again, it reverts to white.
Hold on, I want to challenge the mechanics of that. If I'm tracking the spot of light on the wall and I put the cellophane on the wall, the spot absolutely turned red. Didn't I just mark the process? Like, wait, so the difference between a real process and a fake one is purely its ability to carry baggage, to transmit a mark or energy forward in time.
Exactly. And in that second example, you marked the wall, not the process.
Oh, I see.
The spot itself couldn't retain the modification. It failed to carry the baggage forward in time and space without further intervention. Because it cannot transmit a mark, the spot moving along the wall is defined as a pseudo-process.
The pseudo process.
It is merely a geometric projection. It looks like a sequence of connected events, but it possesses no actual causal capacity of its own.
But wait, doesn't the mark method inherently rely on counterfactuals?
You caught that.
Yeah, because you have to ask, would the spot have remained white if I hadn't put the cellophane there? Relying on hypothetical scenarios about things that didn't happen seems like a massive philosophical vulnerability for an empiricist who demands observable facts.
Yep. You've identified the exact flaw that troubled Salmon himself. And it's why the theory underwent a critical revision. The reliance on counterfactuals was incredibly messy.
So how did he fix it?
Well, a philosopher named Phil Dow recognized this and proposed a brilliant solution, which Salmon actually adopted. It's called the conserved quantities approach.
Conserved quantities.
Yeah, Dow argued that we shouldn't define a causal process by what it could transmit under hypothetical interventions, but by what it actually possesses at every moment.
We ground it entirely in hard physics.
Precisely. A genuine causal process is one that continuously transmits a conserved quantity, a fundamental property defined by physics, such as mass, energy, linear momentum, or electrical charge.
So the beam of light from the spotlight is a causal process because it physically transmits photons, which possess and carry energy.
Yes.
And the spot moving along the wall transmits zero mass, zero energy, and zero momentum. It possesses no conserved quantities.
Boom. By shifting to conserved quantities, Salmon completely eliminated the need for hypothetical counterfactuals. Causality becomes a strictly objective physical fact.
Okay, this builds an incredibly robust, mechanistic definition of a cause. We have physical processes transmitting conserved quantities, interacting with each other at conjunctive forks.
It's a very solid framework.
But how does a framework this reliant on observable physics help us understand phenomena we fundamentally cannot see? I mean, the history of science is the history of discovering unobservable things. If we are strict empiricists demanding physical evidence, can we confidently assert that unobservable entities like atoms, electrons, or magnetic fields actually exist?
If we connect this to the bigger picture, Salmon considered this the key question of scientific realism.
Okay.
And his answer was absolute. Yes, we can and must believe in unobservables, provided the causal structure demands it.
How does he prove that?
He returned to Reichenbach to illustrate this with a really profound thought experiment called the cubical world.
Right, let's walk through this. Imagine a world enclosed entirely within a giant cube. The inhabitants live inside, and the walls and ceiling are translucent.
They can't see out.
Right, they can never go outside, and they can never see through the material. But outside this cube, there are flocks of birds flying around. Due to an external system of lights, the shadows of these birds are projected simultaneously onto the ceiling and one of the walls inside the cube.
Okay, so the inhabitants see a shadow bird fly across the ceiling, and at the exact same moment, they see a corresponding shadow bird fly across the wall.
But the actual birds are completely unobservable to them.
Exactly. But a scientist inside the cube begins mapping the frequencies. They observe a flawless, rigorous statistical correlation between the movements of the ceiling shadow and the wall shadow.
And this requires Bayesian probability. The scientist inside isn't just making a blind guess. They're updating their prior beliefs based on the objective frequencies of these shadows moving in tandem.
Yes, they apply Bayesian inference to realize the sheer statistical impossibility of these complex shadow movements correlating perfectly by pure, independent chance.
It's the mumps all over again.
Exactly. It triggers the conjunctive fork. The mathematics of the correlation demand that the two shadows do not cause each other, but must share a common cause.
And even though the scientist can never observe the physical bird outside the cube, the Bayesian probability combined with the causal structure proves the external bird must exist.
Right. The common cause principle is the logical bridge from the observable shadows to the unobservable reality.
And this isn't just an abstract philosophical game. This maps perfectly onto the most critical discoveries in scientific history.
Oh, absolutely.
The source specifically highlights the French physicist Jean Perrin in 1912. The physics community was deeply fractured back then over whether atoms were physically real or just, mathematical model.
A neat little accounting trick.
Right. And Perrin ended the debate by studying Brownian motion, the erratic, seemingly random dancing of microscopic pollen grains suspended in water.
He realized the pollen grains were acting exactly like the shadows on the wall in the cubicle world.
Yes. Perrin deduced that the visible dancing of the pollen was being caused by invisible water molecules violently colliding with them. By meticulously tracking the movement of these observable grains, he was able to calculate the exact mass and number of the unobservable molecules striking them.
He calculated Avogadro's number.
He did, but he didn't stop there. He calculated Avogadro's number using Brownian motion, and then he calculated it again using alpha decay, and again using blackbody radiation. He used 13 fundamentally distinct independent experimental methods.
That is just the ultimate macro-level conjunctive fork.
It really is.
Perrin presented the scientific community with 13 different shadows moving in perfect mathematical harmony. It is statistically inconceivable that 13 independent, flawed experimental methods would accidentally converge on the exact same fundamental constant by chance.
The math left no room for doubt.
None. The only rational causal explanation was that the invisible atomic realm possessed physical reality. Perrin's methodology, rooted entirely in causal logic, forced the world to accept scientific realism.
So what does this all mean? Wesley Salmon spent his life tearing down inadequate theories to show us that genuinely understanding the universe requires exposing its inner mechanics.
Yeah, you cannot just rely on statistical correlations.
You cannot just predict the storm by watching the barometer. You have to locate the physical processes, the entities transmitting mass, energy, and momentum, intersecting at causal forks.
He demands a highly objective, mechanistic view of reality. It serves as a permanent reminder that correlations, no matter how predictable or robust, are merely symptoms pointing toward a hidden mechanism we just haven't found yet.
So the next time you're presented with an explanation, whether you're reading a study on a new nutritional supplement, or sitting in a boardroom analyzing a sudden drop in quarterly revenue, or troubleshooting a failing piece of software, ask yourself, are they just pointing at the dropping barometer?
Have they actually found the drop in atmospheric pressure?
Right. Have they identified the real physical process transmitting the causal influence, or are they just tracking a pseudo-process moving across the wall?
It is arguably the most powerful critical thinking tool you can possess. However, to fully respect Salmon's intellectual honesty, we do have to acknowledge a fascinating caveat he admitted to late in his career.
Oh, the psychology caveat.
Yeah. While his conserved quantities theory is practically bulletproof for the physical sciences like physics, chemistry, and biology, he harbored deep doubts about whether it applied to human behavior.
He admitted he wasn't confident his mechanistic framework could explain psychology or sociology. He essentially stated that he couldn't commit to a fully reductionist view of the universe without an acceptable solution to the mind-body problem.
Which he didn't believe he would see solved in his lifetime.
Right. It leaves this enormous, profound door open at the edge of his philosophy. Physical causation flawlessly dictates the atomic base of the universe, but the human mind might operate on an entirely different architecture.
It's a huge open question.
And that is the lingering question we want to leave you with today. Think about your own choices, your own intentions, and the complexities of human consciousness. When a friend makes a surprising decision and you try to explain why they did it, are you tracking conserved quantities of energy in their brain?
Probably not.
Right. Or do human intentions, societal pressures, and the mysteries of consciousness operate on entirely different kinds of causation than atoms and red spotlights? When we try to explain each other, are we looking at the storm or just another shadow on the wall, something to explore on your own?